All right, welcome back. Bayesian psychometric models. We're actually getting into STAN today. As I mentioned prior to this recording, I overpromised the last time that your life would change, and then we never got to the life-changing part of class. But today, life is changing for everybody. So we're going to dive right in. And in diving right in, I'm going to, of course, refresh our memory about what we talked about last time. So last time we started describing Markov chains. And we started talking about words like time series plots or posterior distribution densities, and then how we assess chain convergence, and making sure that our Markov chain had run enough iterations to where our posterior distribution looked to be fairly stable, fairly well behaved. I'll put it that way. The posterior plot should be smooth, relatively smooth in the shape of its posterior distribution for parameters, and the time series should as well should be flat effectively with chains right on top of each other. Today we're going to put that to practice, and the example that we left off last time is where we're going to put that into practice, this diet data, where we have, again, an outcome variable that's weight in pounds that we're trying to predict by two variables, a person's height in inches, and a person's diet group that they were supposedly randomly assigned to. Now, again, I'm going to caution you to think that there's no way possible these data could be real. You're going to find that out once we look at the R-squared for everything. But let's envision that being the case. And again, we'll kind of keep it simple to get going. Do you have any questions for me before we begin with today's discussion, though? Anything about last time you'd like some clarification from? Or anything. Life questions in general as well. How about those 49ers, huh? I mean, they played before the last time, but all right, I'll stop talking football. Okay, let's move forward. All right, so you remember we were going to fit an analysis. This is an empty model right here where we predicted the weight in pounds with just an intercept. It's a silly exercise, but it does serve for a foundational model to describe very briefly some of the quantities for what we build for a Markov chain, how we build STAN code. So it's very basic in many ways, right? You would never run a model. You just estimate a mean and the standard deviation. But this serves to help us minimize the complexity of the STAN code to begin with. But by the end of the class, we'll have many more features to it, and then we'll ramp up that STAN code even more as we go forward. So here we would expect the mean to be 171 to 3 decimal places. That's pretty darn good. And then residual standard deviation of 49.52. I should note also you can follow along with the R syntax that we have right here as well. This has all the analyses as well. It's the R file, not the QMD file. So whatever you prefer, you're welcome to flip back and forth for and how we do things. All right, moving forward, I wanted to start with the concept of a model we're building, and I want to think about a path diagram. I mentioned path diagrams because many of you, I think all of you, have taken some other psychometric course to be here. Depending on the course you've taken, you may see path diagrams. Certainly in SCM we see those. But path diagrams can exist for any type of analysis, any type of model, and it gets into terms like Bayesian network or otherwise. There's all sorts of fancy terms for these types of things, when really they're just regression coefficients. So if we were to make a path diagram of this, it would look something like this. Let me flip over. Right, we have our y. This is our, well, hello, hold on here. Why am I not able to draw? Okay, I guess I can't. Never mind. All right, so cannot draw on top of this, but weight in pounds is our dependent variable, right, the outcome. These are our height in inches and diet group are potentially predictors, and maybe we have an interaction between height and inches and diet group, which actually forms a new predictor. It's hard to denote an interaction in the path diagram. If I were to be able to draw on this, which unfortunately I can't, we would put arrows between each of the height in inches diet group and the interaction pointing toward weight in pounds. And the idea for this in the path diagram is a lot of Bayesian models, first of all, use depictions and arrows and stuff, and a lot of psychometric models do. So it's just to get us thinking about the modeling choices that we make and how we build it. Let me actually try one other thing. I believe I have in here my diagram. Actually, I don't believe I have my diagram in there. And then, okay, maybe not. I think I can go down here. Okay, so actually, I'm going to invent the path diagram right in front of you right now. This is really what it should look like. If I uncomment out these portions of the syntax and I push play, what you should see is the following. That is what it looks like. Did you see that all right? So yes, when an arrow in a path diagram, what the arrow indicates is what is predicting and what is being predicted, right? So in this case, weight in pounds is being predicted. You'll see that an arrow that has an arrowhead that terminates a connection, an edge between another variable and it, shows the direction of prediction, right? So height in inches predicts weight in pounds, or diet group predicts weight in pounds, and so forth. Now again, the interaction term is interesting because it's actually a different variable altogether, even though it's highly related to two variables, right? But you don't depict an interaction on a path diagram very easily because there's no real way to show an interaction like a multiplication effect. This is really a linear model effect itself. So, any questions on any of this? This is just me getting you prepared to see path diagrams as we go forward. We may not have a lot of these as we go forward. But path diagrams are a fairly big part of what we do. So there we go. All right. So what are the steps in an MCMC analysis? First step, specify a model, right? We sort of did that on the previous slide. Even though the model itself was not there, we're going to say y is plausibly continuous. We're going to fit a linear model where we predict y, predict its mean, and it has some type of residual variance. When we specify the model, we need to know what are the parameters of the model, because we need to specify prior distributions for all parameters. This is probably too much information at the time, but good Bayesian practice is explicitly setting those priors. Stan, by the way, will not make you specify priors for all the parameters in the model. Right? It'll assume certain parameters follow, I believe, uniform distributions if you don't specify them. So I want you to get in the practice of writing the model down, because writing the model down will help you account for each of the parameters in the model, which will help you specify the priors for each of those distributions as well too. We need to build model syntax in Stan or in whatever program that we're working with. We need to run Markov chains. In fact, we run multiple Markov chains. I personally like running 4. I'll tell you why in just a few slides. You could choose that. Many people disagree about how many to run, but more than one is certainly a uniform standard. But in running a Markov chain, as we talked about last time, we have to specify the warm-up or burn-in period. Remember, that's the period of the Markov chain where parameters are likely to be far away from the center of the posterior distribution. They're sort of in transit, if you think of it. This random walk, they're literally working their way toward the center of the distribution. They're doing so jointly. And then we also have to specify, once we get past burn-in, how many times do we want to sample from that posterior distribution as well too. And then we evaluate chain convergence. So evaluation of chain convergence is important, and it turns out we need to make sure each parameter is converged. There are ways to do that quickly, there are ways to do that slowly, but we'll talk about that as well. And then finally, once we get through steps 1 through 5, we can interpret and report results. And you're probably thinking to yourself, why on earth would I ever run a Bayesian model? Just wait till we get started. It's fun. No, I'm just kidding. It's actually, I like the steps in this. It is just a way, there are cases to why you want to run a Bayesian model. We'll get back to that later, but I think we mentioned this in the beginning. Either philosophically you believe in Bayesian statistics, or there's some other feature, like the model that you want to run is too complicated to run elsewhere, or you want to have the ability to put in prior distributions on parameters as well too. So let's start with an empty model. By the way, any questions so far? I should ask. No questions. I like it. All right. So let's start with an empty model. All right. So here, weight in pounds for a person is predicted by just an intercept and then an error term. All right. The error term represents the distance between where the intercept is in each observation itself. So here, error, we would say, follows a normal distribution. where the mean is 0 and the variance is sigma squared error. Sometimes we call this the residual variance. In R, what I had shown on the previous slide, we had residual standard deviation. The LM function in R gives it in standard deviation. It's just the square root of the residual variance. So let's ask some questions that we have to think about when we put a model down. What are the variables in this analysis? So term variable refers to data, right? Weight in pounds, that's right. Weight in pounds is one variable. There are no other variables in this analysis. Everything else is our creation for model. All right. Next question. What are the parameters of this analysis? What do we have to estimate? There are two. We've been sort of talking about them the whole time. Oh, balloons. I like that. Gosh. For those of you who don't see my video on the YouTube, if you will, first of all, like and subscribe. The merch is coming. But second, I'm making Apple what are these called? I don't know. Hand gestures, and we're having all sorts of confetti and balloons about parameters, distracting all of us. Anybody want to take a shot? There's two parameters. I'll just say it. Two parameters, right? There's beta 0, which is the intercept. And there's sigma squared error itself. Right? Depending on how you view things, you can get into nuance and say, isn't error itself a variable that we don't observe? You could consider it that way. And if that's the case, this is a prior distribution where we're estimating one of the parameters. But let's not go there for right now. Let's just leave this as is. Okay? Okay. Welcome to Stan. It's now time for Stan. Stan, as you know, estimates MCMC Markov chains. It's a Bayesian estimation program. I believe it to be the most convenient. I think it has many very good, or most recent. First of all, I wouldn't say most recent now. I should probably change that. There's all sorts of packages out there. PyMC in Python. Nimble in R, and anyway, there's no shortage of MCMC if you want. I like Stan. I think it's heavily invested in by Institute of Education Sciences among other funders. I think it's done a good job with error messages. Like, for instance, I taught this class in JAGS in 2019, and the error messages are so cryptic, really hard to troubleshoot. Stan does a little bit better job with it. You may not feel that way to begin with, but let me tell you, it's actually, once you get used to it, it is very informative. It does more than just Bayes. It will actually do maximum likelihood. It'll do variational Bayes. For those of you who took generalized linear models with Lisa Hoffman, do you remember how many packages you had to download and install in R? I remember talking about this with her. I keep telling her, use Stan. You can use ML and Stan. Build a function, build a package like that just codes it. And she's like, oh, no, definitely not. All right. So you create a model in Stan using Stan's syntax. This syntax itself is just a text file, just straight plain text. That plain text then gets translated by Stan to a custom-built set of syntax in C++. C++ is a high-level programming language. I think it's high-level. I wouldn't say it. It's a programming language, right? C++ is very, I would say, difficult to develop in unless you're really fluent in it. But what it does is it allows it to be built, compiled into an executable. Just an executable is a program that runs on your computer. It's a standalone program that's specific to your model. So why this is the case, I think I mentioned this before, but I'll repeat it. When you create general estimation software, there's an overhead to being general. It takes a lot. And Stan is super general. You can run a lot of different models in it. But that they try to remove that overhead, basically the amount of code internally to software that needs to be executed to do this generality, by shortcutting it into making a very custom, not general, executable for your model. So it turns out every time you run a model in Stan, you're building a very custom program specific to that model itself that resides somewhere on your disk. Now, Stan, by default, puts it in a temporary folder or a hidden folder in a place where you don't normally find it. But you can find it, and you can see it, and you can run it standalone if you wanted to. You can run it with a different program. You can run it with a different... You can connect all sorts of different statistical software to Stan itself. That is the catch for why Stan becomes a little bit faster. You then run the program to estimate your model. If you use R, the interface can be seamless because you end up seeing Stan run right in the console itself. The output from Stan gets printed to the screen. You wouldn't know that you're calling an external program to run it. I will also say this, we're using R in this class, but Stan has interfaces with a whole bunch of other programs as well. For instance, this is the website for mcstan.org. And let's see here. You can connect Python, you can PyStan. There are other connectors to other stat software, although I'm blanking on where those are located right now. So you don't just have to use R. If you're familiar with other programs and packages, you can call Stan from them as well too. How are we doing so far? Any questions? Okay. Wow. I should have an image here. What did I do wrong? Stan and RStudio. I didn't show you the image. That's why. Goodness. Hang on here. This is what I wanted to show you. It should be on there. If you're in RStudio, you can actually create a Stan file under the File menu right here and go to New File, and you'll see Stan file listed right here. It will create a Stan file that has a little bit of coloring for the different options, some built-in language, some others in Stan itself. So RStudio has Stan integrations built in, which is nice. It does syntax highlighting as well, and which I find is very helpful. Although I will say the syntax highlighting in RStudio is somewhat suspect. You can also build... So basically, again, the Stan syntax itself, if I go back over here and I just show it a file, this new file that is created right here, if I were to save it, it saves as just a text file. And all this is plain text itself. It usually it ends with a .stan. And like other R packages, that just means you can take this plain text and you can embed it in a quote in R itself. So if you go into some of my code, what we'll see here is I create a Stan model where I create an R object and I set it equal to a character string. Right? This just returns an object. If I were just to run this section of syntax on line 60 all the way to the end of the quote, what you'll see is Stan model right here is just a character. It's just a one element character vector. I'd have to use the cat command to show it. That's all it is. So it turns out you can access Stan by creating standalone files or creating syntax in R itself. And what I would recommend for you to begin with is the standalone file, because it'll help color code the syntax. It'll highlight syntax until you get used to what you're doing. Once you are fairly used to what you're doing, going back into R and putting the character string is great, because then you only have one file in your whole analysis. Whereas every time you want to create a new model or a tweak on it, it takes another Stan file. And so for those of you who've used M+, where there's only one file per analysis, and if you're doing 15 analyses, next thing you know, your folder has Model 1, Model 2, Model 3, and if you're like me, Model 4, final, and then there'll be, oops, Model 5, Model 6, Model 7, final, right? That type of thing. You want to get into file hell, you can modify that. Now, there's one other feature I want to note. This is RStudio. Turns out you can run R from all sorts of different programs, and the other program I would recommend, if you're trying to get used to Stan, is Visual Studio Code. I don't know if any of you have used VS Code before. It's a general program for coding in general. I mean, like it has a bunch of extensions to it. I will recommend the program VS Code that's on your desktop, and if you want to see more of it, I'll be happy to talk more about it at a later lecture. But VS Code has an extension that someone has built that I find to do better syntax highlighting in Stan. So if I go to my Stan file here, the blue character, the aqua color are the names of blocks of Stan code that we'll talk about in just a moment. The blue are words, keywords in Stan. And then, of course, the light green are comments as well. Vladimir, yes. Great question. That is a great question. So RStudio builds just direct to R itself, right? Because VS Code is a bit more general, you actually have to attach R to it. And the way we attach R is to go into an R file and we start running code. You'll see that we actually have an R instance over here that runs code. And if we want to see the objects in the environment, we can go into the R tab. Now this is an R extension that's built from VS Code. And in that global environment, once I get to the place where I'm installing. I shouldn't do that. Anyway, let me see if I can get there real quick. Here we go. You can see the R environment here, and you can even click on objects and see them as well too, if you've got it coded. I found and the thing about VS Code. So here, if you're in the notebook site. If you're not through our class automatically just gives you RStudio. There's no other option. But if you go through the general notebook site, if you have your own account on IDAS, what you'll find is there is a VS Code button. I don't use that one as much because this is something, it's an open source version of VS Code called Code Server, and the extensions aren't the same as the one that you would install on your desktop. The one on your desktop you can get for free. I'm happy to, if you'd like to know more about this, I'd be happy to give a lecture on how to use VS Code for what we do as well too. I'm just putting it out there because I found it to be a little bit better at syntax highlight. It does other things worse as well. And finally, the other reason I really love it on my own computer is if you want to code and code fast, there's this thing called GitHub Copilot that integrates with it on your local machine, but not on the IDAS server. And so there you can put comments in and it will suggest code. It's not right a lot, but if you're doing highly repetitive tasks, it will be pretty quickly honing in on what those repetitive tasks should be. For instance, earlier this week, I was creating a set of slides for a conference I'm going to at the end of next week. And it turns out I needed to build a very long set of effects for an indirect effect in this very complicated path model. Long story short, there's 27 different parameters needed there, and I needed to do that for 3 different effects. Well, I put the first one in, took a little bit of time, and the second and third it suggested, and it was right. I was like, oh, that's nice. That goes faster. So anyway, too much information. VS Code can be your friend as well too. Any questions? All right, I'll leave it for now. Okay, so let's take a look at Stan syntax. Here, Stan syntax, this is the actual syntax that we would use for our model. I have it just in our my Quarto slides. You can find it in the R version as well too. But each line in Stan is like SAS, M+2, right? You need a semicolon to terminate a line. And then comments in Stan start with a double slash. So unlike in R, where you use the number sign, the pound symbol, hashtag for comments, double slash are comments. This is the inline comment that you would see in C++. That's how it works. Stan syntax works in what are called blocks. And I don't know that it's cut off on the screen here, which is funny because I worked hard to not have it cut off, but I'll just tell you what shows up here. So a block of Stan syntax is as following, right? Data is a block, parameters is a block, and model is a block. And for me, it's kind of in reverse. These sections themselves, data as you would expect, this is data that Stan will receive, that you'll be sending into Stan to do the analysis itself. So this does include your outcome variable, which we have here, but it will also include other details about the data that you may need to tell Stan in building your model. So I put in here the number of sample size, but it turns out I actually don't need that in anything that I'm doing here. But long story short, data doesn't just have to be a data frame. And here's the hardest thing to envision. I know I say this because if you're used to other classes, you get used to software and data being a very certain way, right? Long files, multi-level, wide files, psychometrics, somewhere in between. Well, Stan is sort of anything goes. So you don't have to have one piece of data coming in. You could actually separate your data into different variables themselves. You don't have to have one data frame. You just think about Stan's input as literally being data coming from an R list object. A list in R is a collection of other objects itself. It's a kind of what we call a ragged array, right? A list can include data frames, single numbers, character vectors, other lists, right? You can have embedded lists and lists. Pretty much anything goes in an R list, and that's how Stan is structured as well too. So data is what you will be sending to Stan, which means when you see this data block in your R syntax, you'll literally create a list, and there'll be an entry for N, and there'll be an entry for Y. And if you don't have that, Stan won't run. How's that sound? So far, so good? All right. If any of you have this option and want to give the thumbs up or thumbs down, I'll be happy to see it too. So you can do this too. How are you doing? Right? Bad. All right. Next, parameters. The parameters are where you specify what is being estimated. So here, beta 0, we know that's one of our parameters, and sigma is the other. The other thing, when you specify them, you have to declare, and actually this is true with all the data as well. In Stan, much like in C++, you have to declare the type of variable that you have in your data. So here, the word real indicates that beta 0 will be a real number, which means a floating point number, in our case, double precision. It will be unbounded, and it will be on the real number line from negative infinity to positive infinity. As such, it can be represented in numeric space. A floating point number, when we talk about that in computer science, a floating point number is one that looks like a real number that has decimals to finite spots, but it's formed through a combination of bits. So it's actually kind of a weird discrete space. Not every possible infinite value can be represented, but so many can. It's about the same. So real is for continuous variables. You can also put a bound on. So we know sigma is a standard deviation. It should not go below 0. So you would put in, what's that? Carets? Is that it? I don't know what those are. Not brackets, not braces, whatever those are, carets. You would tell it the lower bound. And then what would happen is Stan would then not estimate or not allow it to be below 0. Technically, what Stan is doing is transforming this into an unbounded space using a very simple transformation, but then it calculates other quantities needed to make sure the density, the likelihood itself, is maintained after the transformation. You will see up in data, vector. Vector is literally a vector of data, like a row or column vector. It is of size n, and that is why I needed n, actually, to be input. It's right below it. You need to tell it how many elements are in the vector. So if y is just a bunch of data coming in from R as a numeric variable, and you have n observations in y, you need to tell Stan how many observations are in to build it. The term vector implies a real number, which means Stan will expect y to be any number. It could have decimal places. It can be anything. Whereas the term int stands for integer. It's another type of data that's common in computer programming. N is a discrete value. Cannot be lower than 0. The lower 0 here is sort of superfluous. We don't need it because you can't have negative n. Furthermore, technically it should be lower 1. You can't have 0n and then send it y that has 0 length. That's not going to work either. But it's just to show you that you can actually put a check in here as well. So basically you can have Stan check your data to make sure it fits the properties that you want it to do. Where that might be helpful is if you're I use Bayes a lot. I use Bayes in simulation studies. I run a lot of analyses that are in batches. And if you put these catches in your Stan code for it to break when data don't come in correctly, you save a lot of headaches later on because you end up making sure that one of the problems that happens is your data isn't structured the way it is. Doesn't happen anymore. For instance, I was, again, running analyses in JAGs this weekend. Why JAGs? I'll tell you later. And JAGS doesn't have this property. And somehow in my R code, I didn't realize I was trying to send it a data set that had zero rows. Great, 0 rows. Guess what it's going to do? Not going to work very well. And I kept getting cryptic error messages. And I'm like, where's the problem in my code? Finally, after 15 minutes of looking at it, I'm like, wait a minute, let me check the data. Sure enough, data had 0 rows. There was a mistake somewhere in the code elsewhere. It would have been nice to have JAGS say, hey, can't have 0 rows. Something along those lines, but JAGS did. All right. Finally, the model section is where the fun part happens. Right? We specify our model for the observed data, but you'll note our model here doesn't look like a linear regression. Right? You have to understand your data, your analysis model well enough to know what you're assuming about y. So from our previous slide of the model parameter itself, we can see with error being normal, the outcome itself should be also normal. And whenever we add a constant to a normal distribution, it changes the mean by the constant. So the mean of that normal distribution should be beta 0, and the variance of that normal distribution should be sigma squared. And if this is the first time thinking about this, about how to structure a model, that's great. This is helping your statistical training more than you realize. Because, turns out, how many of you have taken a class from Lisa Hoffman? I keep talking about Lisa, but, you know, she probably hears me. Yeah. She talks about the model for the mean and the model for the variance. You ever heard that before? Well, it turns out the model for the mean shows up in the mean of the normal distribution. That's why it's the model for the mean. The model for the variance shows up in the variance part of the normal distribution. And here, I will note that sigma is the standard deviation, and that's a choice. Stan's user manual defines the normal distribution to have a standard deviation here, not a variance. But their standard deviation is square root of variance, so it should be okay. So here in the model, we're defining y to be normal, follow a normal distribution. And so what Stan will do in the model data likelihood is use the normal PDF. The mean of that PDF will be set by the current value of beta 0 in the Markov chain. The standard deviation of that PDF will be set by the current value of sigma in the Markov chain. And the likelihood from it will be based on what the data happens to be. So what you're specifying here are the part of that Bayes theorem, the model data distribution, the model data likelihood is what I usually call it, the likelihood of the data given the parameters. Then just above the model, I put the prior distribution. So beta 0, I might pick a normal prior for beta 0 with a mean of 0 and a standard deviation of 1,000. Now that seems highly specific. Why 1,000? This is where the setting of the priors becomes more practice than anything else. If you think about our data, we know in this basic model, the mean should be the mean of the data, and we know these are weights in people, right? So I would expect people's weights to not be, to be what we would normally expect them to be. Somewhere between, I don't know, these are adults, somewhere between 80 pounds and 400 or 500 pounds, with the center of that being somewhere in the 100 to 200 range, right? So if you're thinking, what is the mean going to be? Where's my belief of the mean? I may not have a prior belief, so I may choose to have an uninformative prior, such that this normal distribution with a prior of 1,000 indicates the width, basically, plus or minus 3 standard deviations. So basically between negative 3,000 and positive 3,000 has 99% of the mass of that. I would call that a very uninformative prior, because in the space where I expect weight to be, it takes up such a small region of that normal curve that the height of it will be roughly the same across that region. So I would call this an uninformative prior itself. Similarly for sigma, I might pick a uniform prior. Now I will tell you, this is a bad prior to pick. Don't ever use uniform. I wouldn't say bad. Nothing's really terminal, but uniform's difficult because you have to say how high it will go, right? I don't know what the standard deviation of weight will be at all. I have no guess. I picked 100,000. It should be less than 100,000. We shouldn't have high enough variation in our weight to where that happens. Even if we went to, even if we had two extremes, we had people who were struggling to put on weight and very low weight, and then people who were obese and trying to lose weight and very high weight, that still probably wouldn't have 100,000. So that's where I picked that number. How are we doing so far? Questions? Okay. So I described these blocks of data, blocks of syntax in Stan sequentially. Data, then parameters, then model. But I will tell you right now, to me, what is most important, when you start with your code, start with model. Because the other two sections depend on what's in model. What do I mean by that, right? Well, if I say y is normal, I know that I need to import y as data. So I can put y down here, and then I can go up to data and put y in data. And I know to call it a vector, I'm going to have to put in n as well too. So model specifies what I'm going to need to name in y. The name of y in data has to match the name in y in model, right? Vladimir. I don't believe there is. I've never seen it work that way. So I just tend to structure my model. I could have gone backwards. I could have put the model first and the priors below. I've done it both ways. So no order that I can hear that I know of, at least for the basics. Thank you. So so again, in the model, I mentioned y. I also define its parameters. Now I call it beta 0. You can call it anything you want. You know, I could have called this Templin 1 or something like that if I was really egotistical. Now, I don't know why I'd want to do that, but if I wanted to, you can call it that. But once you call it that, you have to define it as a parameter with the same name, right? And you have to give it a type of data that should be expected in the distribution, which we'll talk about in a little bit. And then you also have to define it with the same name as a prior as well too. So the model to me is sort of the key to all of it. And if you come to me with Stan code that doesn't work, the first thing I'll ask you to show me is not data or parameters, it's model. Cool? Okay. Next on the list, there are actually 3 other sections of Stan code blocks. And I'm not going to talk about them yet, but they will come up later on. One's generated quantities, one is transform parameters. I'm blanking on the other one. Anyway, we will use those very shortly as well too. And you can also, there are other features as well. Stan has a whole host of distributions. I've got normal, I've got uniform. You can see there are different colors, so the color code has come through. The syntax highlighting. You can even define your own distribution as well in Stan too, with another block of syntax for a function. So there's all sorts of ways that you can build in Stan. How are we doing so far? Okay, I think the other section I'm blanking on is transform data, if I'm not mistaken. But anyway. Okay. So I just mentioned all this. Here you go. These are the types of numbers. If you want to see where this is coming from, oh gosh, I should stay on this page. I have a link to the reference manual, and you can see in the reference manual a whole bunch of types of, and actually this would be the functions reference right here. And the functions reference, once you get down to discrete distributions or continuous distributions, these are the distributions that are built into Stan. So if you know that, for instance, I knew my y was going to be continuous because I want to use a normal distribution, I click under unbounded continuous distribution, and sure enough, the normal distribution shows up there. It tells me I specify it in this terms in syntax, where mu turns out to be the mean, and sigma turns out to be the standard deviation. And that's why I knew I needed to code the standard deviation as sigma. Now, if you're familiar with probability densities, that's great, but always go back to the distribution, because a simple thing like this, in Stan, sigma is the standard deviation. In JAGS, in the normal distribution, it's not sigma, it's actually something called precision, which is 1 over the variance. So why I say that is someone else writes the software, they write it in their own context, which matters to them. Not everything's uniform. Even though you're familiar with the distribution, you may be familiar with the distribution, you may want to see it. I encourage you, in fact, I even do this. I've been using Stan for quite some time now. I do this even when I code now. I have this link up, I bookmark it even, and I go and figure out what I need to put in the distribution itself. The other thing that you're going to see here is that there are a bunch of other normal functions that come with it as well. We'll get to these as we go later on, but you can generate normal data. There's standard normal. But the other part that's important here is to understand when you specify a built-in distribution, you have to specify the parameters of it to be the right type. What I mean by that is mu has to be a real number. That's what this is right here. And sigma has to be a real number that's strictly positive. That's what that means here. So if you don't put that in, there's likely to be some type of error in stan as well too. All right, questions? Okay. Mentioned this before as well. I'll have to go through that. Then, once we have our syntax together, we need to compile the model, right? So if I go over to my R section right over here, if I go, one moment, I don't have diet data in my file. Oh, that's too bad. All right, I guess I won't have, there it is, it's right here. That's why. All right, wrong working directory. There we go. To give you a sense of what's happening, I just wanted to get to where I could show you stan itself. So our stan model, if I built this in R, I could have it as a quote string, as I mentioned. I could also have it as the standalone file, but I'm going to show you both methods here, right? The file, if you look in my files, I have this model00.stan. First of all, let me ask, is the font on my screen big enough for you to see on your screen? Do you need bigger font? You're good? That's good. I know you can zoom in on Zoom on your side if you need to as well, too. Okay, so this is the model that I just showed you. This is a standalone text file. To compile it in R, I run this command, cmd model itself, and I tell it what the name of the file happens to be. And because my current working directory is the same as what you see in the file section of RStudio, I don't need to tell it the path to the file. So if I run that, what you will see is, oh, model distribution. Model executable is up to date. So I wanted to show, let's see here. Nope. Let's see if I can change it just for a second here. I make a change. There it goes. It says compiling stan program. This is literally, for those of you who had an issue with or had to think about R tools, it's using a free version of a compiler, and it builds the program itself. And now you'll see in my directory I have this model00 executable. This, by the way, is built on a Linux system, so you won't be able to run it on a Windows or a Mac. Got to run it on Linux, but it's built custom for the model itself. That's the model I was telling you about. You can even find the location of it. It's sitting right there. In general, particularly when you go to build a model when you don't have a file, it will move the location otherwise. So let me just show you how that works. Make sure I'm not repeating anything here. When you go back to, if you want to build, so let me back up. This is when you have a standalone file. The stan file function is just called model00.stan. If you don't want to use that method, if you want to use the built-in quote, where I have stan model here being an R character vector, you tell the option in the cmd stan model function, you put a function called write stan file around, and it will literally create a text file with that in it. So it is making a text file somewhere on your machine. So I can just create right here, and it compiles again. That waiting that you're having there is literally C++ being transformed into an executable. And the location of this file now, the location of my executable, is in a temporary directory. So the difference between the two is if you use a standalone stan file, it will build the stan executable in your directory where the file exists by default. And if you don't use a standalone stan file, it will create a temporary directory somewhere and put everything there. How are we doing so far? Okay. Next, I will say, if you use, so there are, I mentioned, and in homework you saw we had CMD stan R, which was the hard one to install. And then there was one called rstan. rstan came first. rstan is not being developed any longer, or not being maintained. There are people who are sort of trying to do that on the side, but it's not really the official one. CMD stan R is the one to use for most of what you do. rstan made it easy, but it also was somewhat limited in how it was built. And so CMD stan R is really what we're going to focus on here. In rstan, it would just handle all this behind the scenes. But I won't talk too much more about that, because the version of stan that rstan runs with, I believe, is 2.21. And we're now at 2.35 or 3.6, depending on the next release. And some of the code is not backwards compatible. So CMD stan R is the one to focus on. All right, so now we have to build our data object for stan, right? You remember in the data section of our code, we knew we were going to tell it y and we needed to tell it n. And the function, the object to use in R for that is a list object right here. Right? So the list object in R you create by using the list function, and then you give it, the arguments that you give it set up the terms of the list itself. So you say n, capital N, is equal to the number of rows we have in our data frame. That's the count of people we have. And you might say y, lowercase y, is equal to the variable that has our weight in pounds in it. Now, this is important. The names of the variables in the list have to be the same as the names of the variables in data. And they have to be, it's case sensitive. So capital N is what stan is expecting, and lowercase y is what stan is expecting. So that is where we build a list. If I run this, if you've never worked with lists in R, if you just type stan data, next thing you know, you put a $sign in, and you can get, oops, with our $sign here, we could plot out n, we can show y. If I just type stan data, you'll see all the elements of the list itself, right? So that is, I just created an embedded list. I'm going to go back and fix that real quick. Okay, questions on lists in R. Many of you are familiar with lists. I don't need, if you do have questions, you're welcome to send them to me later on as well, but lists are how we run stan in R. So now we're finally ready after we have our list of data. By the way, if you are using rstan, the list is the same between the two. But now in CMD stan R, we are now able to run the Markov chain. And so we use, we end up using, so it's interesting, when you build the executable in stan, so right up here, model 00 from file, turns out that is an R object, right? So if I go and investigate what's in the R object, if I ask what type of class it is what's called a CMD stan model, and it's an R6 object. Have you ever heard of R6 for an object before? Ever heard of S3 or R4? Never heard of those? Or RCs? Okay, so it turns out in R is so open to any type of structure that anybody can create an object structure. And R6 is a type of object in R that contains data, very much like the other data objects you have. But a couple of the features of R6 that are nice is that whenever you call a function, it doesn't, whenever you call a function in R, it actually makes a copy of your data. It's called passing by value. So anything that you send into the function, it makes a copy of on your disk, which takes up more time and more space. An R6 object passes data by reference. So basically the data exists on your machine. They all have a location. It passes the reference to that location. It's sort of an advanced, a little bit more advanced concept than what you're used to. It runs faster. But what that also means is in R6, to call a function on itself, you can actually call a function for it. So this $sign will allow us to do that. So it turns out to run our analysis, there's a sample function built into our R6. So when we compile a stan code in R, it knows where the executable is, and it knows how to access it with this function named sample. So in sample, we have to tell it the data. We have to tell it a random number. seed. So remember, in Markov chains are simulated values. And those simulated values come from pseudo-random numbers. We call them pseudo-random because given a seed value, we can create a string of what looks like random numbers. If we lose the seed, we won't be able to see what that string happens to be. But for every seed, there's the set value of random digits, right? It's this process of random number generation. So our seed, we give it a seed. I gave it seed number 1. You can make a seed where you want. That should give you replicable results, although replication is difficult, and even the Stan manual says it. It is. We have to specify the number of chains. I'm going to specify 4. Again, I'm going to tell you why in just a moment when we get to evaluating convergence. CMD Stan R will also run in parallel, meaning each one of these 4 chains will be run at the same time so long as you have 4 different processors. That's convenient, right? So in theory, it shouldn't take much more time than running 1 chain if you have 4 available processors. It turns out on IDAS, we actually have quite a few processors. Let me see here. In the parallel package, there's a function called detect cores. Cores are processors. We have 128. So in theory, we could run 128 chains. That's overkill. We don't need to do that. I don't think. Okay. Finally, we tell it the number of iterations we want for warm-up. Remember, that's the period of sampling when the parameters are starting at the random values and taking a random walk toward the center of a posterior distribution. So I said 10,000. 10,000 is probably overkill for this as well, too. We'll talk about that in just a moment. Iteration for sampling being 10,000 as well. So that's after you get through the first 10,000 steps. We discard that part of the time series. We don't even look at it. We keep the remaining number of steps, and that's called the sampling window, the sampling period. And that's, we want 10,000 samples effectively is what we're looking for here. Questions? Anything question? I'm going through this a lot. All right, so now the same thing works in RStan. I'm just going to pass over that real quick. The MCMC process itself runs a series of discrete iterations. That's what I was talking about to begin this class. Each iteration allows each parameter to change its value randomly, right? So for each parameter, a new parameter is sampled at random from the current belief of the posterior distribution. Depending on how much you want to hear more about sampling or what's under the hood for these models, I have lectures prepared if you'd like to see what's under the hood. But the specifics of how they're sampled, I talked a little bit about last time with Gibbs sampling versus Metropolis Hastings, but those are available. We can talk about that later. In Stan, which uses Hamiltonian Monte Carlo, for a given iteration, a proposed parameter is generated. That process of the proposal is actually pretty interesting. It uses Hamiltonian dynamics or physics to figure out, using a particle parameter to figure out where a good draw would be. The posterior likelihood values are calculated for the current and proposed value of the parameter. Right? We talked about that a little bit before. And the proposed values are accepted based on a draw of a uniform number compared to the transmission probability. So for every step, we get a new parameter. We calculate the probability we should move from our current parameter to our new parameter. And if a random number happens to fall under that probability, we move. And if it doesn't, we stay. So a lot of times you'll see, particularly early on in Markov chains, when the random process isn't very good, it starts throwing out values that make no sense, and those get rejected. So if you look at a time series of a parameter as it starts, it might look very flat. That flat part is the parameter being, the proposed value is being rejected at every iteration. Like this. Here you go, flat parts. But let's talk about it. Let's see here. Let's run our model, shall we? So we run the model. That's quick. You see all this right here? It's reporting iterations at every 100 iterations itself. Because we had 10,000 warm-up, 10,000 sampling, we had 20,000 total iterations. It tells you what percent of time it's done. It happened very fast. And what we can do then is start to look at the values. So the values themselves that I have here, the model 00 samples right here, these values, make sure I don't have that. Yeah, these are the estimates right here. Right? So we saw in our frequentist version, the LM function, the beta 0 was 171.000. We're 171.01, so very close to it. Sigma is a little different. 51.77 is what we have, whereas I believe it was like 49 something or other before. And I'll get to why that's different in a little bit, but it's basically how we summarize. Part of it's how we summarize our posterior distribution. Part of it's the process by which we derive sigma. Questions? So convergence, again, is what we need to evaluate. And I mentioned just a second ago that you may see early on in the chain a very flat part. Right? I literally ran this chain. I threw away one iteration for burn-in. So this is literally iterations 2 through 100. These are the 4 different chains of beta 0. Look how widely divergent they look. Right? But something's in common with each of them, right? Very few times does a value go away from. Now, we know 171 is where we sort of ended up. We know that ahead of time. In complicated models, we won't know that. Right? So this area right here where my arrow is where the chain should be moving toward. And what you see in the beginning, this flat line for this dark blue right here, that means iterations 2 through right about 21 were rejected. Nope, right? Bad idea. Don't want to have that. Usually values that were far outside where they should be. But eventually, again, running the chain long enough, the next thing you know, we start to move in the right direction. And yeah, there might be a case where we move in the right direction, but we come back a little bit. We keep moving in the right direction. You can see what we're end up getting to within 100 steps, 100 iterations. We're pretty close to the region where the posterior has its center of mass. To me, that's pretty neat. We literally started all 4 parameters somewhere between -2 and 2. And by 100 steps later, they're right around 170, 171, which is where we want them to be. I think that's magic. I don't know. Whenever I see that in estimation, I'm like, yeah, that's the way it's supposed to work. That looks nice. But I'm wired differently than all of you. I understand that. What do you think of this? Do you think this kind of cool process? Look at variance, right? It started very close to where it would be. One of the variances went really high. That's chain 4. And chain 4 is related to this other line right here. Well, that variance is probably going to be high because chain 4's mean isn't close to where the center part of the mean is. And so when you think of the normal likelihood, the likelihood values that are closest around the mean, so it needs a high variance to kind of even out. The data aren't telling the mean to be there. The variance is the only option for it. But then quickly after that, it comes back down to where it should be, and by 100 steps, the variance is well behaved as well too. And I will say the variance absolutely has an uninformative prior on it because that prior is uniform, right? So that's bad convergence. And then if we were to go and make densities out of that, you'd see this, beta 0. This is not a converged model. You can tell that, right? Time series doesn't look like that. Well, this whole thing that I'm doing here is something called the idea of examining chain convergence, right? Once the model runs and stops, the next job is to determine if the chains have converged to where they're being sampled from the center of the posterior distributions. Sometimes we call this convergence diagnostics or convergence diagnosis. There's a long-running package in R called CODA. One of our former colleagues here at Iowa was one of the co-creators of it. Professor Cowles, I think her name is. It goes back to the 1990s. That's how useful it is. We've sort of updated it. It still exists, and it's actually quite useful as well. But there are many methods to evaluate chain convergence. There are 2 that I really prefer. One is the Gelman-Rubin potential scale reduction factor, and one is visual inspection. And this is a typo. Should not be a space between in and inspection. Inspection, I don't believe, is a word. Maybe it is. Who knows? I do stand, not English. So the idea behind this is we can look at a plot and say, yeah, that's not converged, right? But we can also calculate statistics by it. And the statistics we calculate, this PSRF, sometimes goes by R hat. I'm actually linking to the SAS user's guide. It describes it pretty well. I love, by the way, SAS I never use anymore. Oh, it's not found anymore. It's funny. It started to load and not found. Well, long story short, PSRF is, we denote it with the letter R hat. It's used for analyses with multiple chains. And what it's calculating is the ratio of between chain variance to within chain variance. Right? It sounds like a multi-level concept, doesn't it? So think of it this way. If between chain variance is equal to within chain variance, what would we see? We should see the chains lining up on top of each other, right? Because between chain variance would be very little, and within chain variance would be also about the same, right? If they're not, that indicates if the between chain variance is bigger within chain variance, we would have an indication that one or more of these time series were not right on top of each other where they needed to be. So this R hat functions a lot like an F test in ANOVA. You've probably heard of, ANOVA's F is between, over, within. Sounds like we're doing ANOVA on Markov chains. And the answer is yes, we are. So what we really want R hat to be ideally is the value of 1, which is actually the expected F value under the null distribution in ANOVA, if I'm not mistaken. My history is a little bit shaken, but that's all right. So when you looked at my output over here, you'll see there was a column called R hat. Right? R hat, from the model I ran, not the bad model with the bad plots, but the good model right here, my R hat is 1 for each of the parameters, beta 0 and sigma. LP is the likelihood of the posterior. That's the model data likelihood itself. It also calculates it as well. We'll use it in other features later on. But here, if I show you what my plots look like, the trace plot, which the Bayes plot package will give us. Oh, where'd it go? It's not going to work. There it is. Okay. This is the output of what I just ran. That literally is the picture that we had at the beginning of the class, last time, right? And this corresponds to an R hat of 1. This is what it's supposed to look like. And with a very simple model like this, you would expect R hat of 1 very quickly. And we see this, right? Questions on any of this? So this column R hat right here will tell you which parameters may not be converged. All right. So now let's talk a little bit about the options for MCMC. So as R hat is sort of the uniform statistic we use to determine chain convergence. We like it because multiple chains being run allow us to see if there's multiple modes in our posterior distribution. And if there's multiple modes, then our result is going to be in question, right? So we want multiple chains. Multiple chains also helps determine the estimate of the between chain variance itself, right? Between chain variance estimate, the more chains we have, the more accurate our between chain variance estimate happens to be. The more accurate our between chain variance happens to be, the easier we can assess model convergence. That's the thought. So when I say I'm going to run 4 chains, I'm running 4. You could say, what's the minimum number of multiple chains I could run? 2. How many of you have calculated the variance with 2 observations before? Kind of tricky, right? How many of you have calculated variance with 3 observations before? Not good, but way better than 2. But let me get to 4. Still not great, but 4 is much more stable than 3 and 2. And so why I pick 4 is, to me, 4 is the first number to which I have a little bit more certainty of that between chain variance, which helps me have a better sense of where R hat would be. I would tell you that many people use 2. I've seen 3 get out there, but I like 4. So I go with 4. So 4 is why I pick 4 chains. You can pick however many you like. I would advise at least 4. Right? So that's one option, which is how many chains do you run? The second option we need to talk about is how long the warm-up or burn-in period should be. Okay? So in our case, the warm-up or burn-in period is very difficult to determine ahead of time. And it turns out we did overkill in ours. Because, as you saw in our plots right here, why was it overkill? Right? Remember, the warm-up period is to take the values of our parameters and move them close to the center of the distribution. Well, within 100 iterations, I can tell you that the variance parameters or the standard deviation parameters look very close to the center of their distribution, just knowing what I know now. And the same thing happens with our beta 0 parameters. They're very close to the center of the posterior distribution. I probably, just to be sure that that was it, I might run 150 or 200 iterations, but I'm guessing it would look the same. And in fact, if you wanted to see that, we could even play around with this a little bit as well too. This is the plot I just showed you. But if I change this to, let's say, 200 iterations, I only have 10 for warm-up actually. Then that's what it looks like after from between 100 and 200, right? So you get a sense that we're pretty close. Now, you see in this section that it's not smooth sampling, right? It's not, like if I were to set the warm-up here to 200 and set the number of iterations, say, to 2,000, it still wouldn't, I don't think, be ideal. Maybe close. It's not bad, right? And if I go to look at how my R hat is 1 there. So what I'm trying to get apart to you here is that the hardest part of figuring out the options of MCMC is figuring out the warm-up period, because you have no idea what it needs to take ahead of time. So that's the tough part. I would say this: the more complex your model is, and some of our psychometric models are certainly complex, the longer that period needs to be. Okay. Finally, the last part of it is the sampling iterations, right? You really want sampling iterations need to be long enough to thoroughly sample that posterior distribution itself. So if I go back to this last thing I ran where I had 2,000 iterations of sampling, you'll see I have these posterior distributions that still look pretty good. They're a little bumpy in places, right? They're not completely symmetric. That happens. It's going to happen. The question is, what do you want to use to summarize it for, right? And this is where we get into somewhat basic statistic concepts, right? We're sampling from a posterior. Do you remember in basic statistics the sampling distributions of parameters? We always talked about, if we repeat this experiment over and over and over again, this is what we get. We've sort of done that. It's a little bit different. We're not sampling data, but we're sampling parameters, right? If we want to then summarize that distribution that we're sampling from, the number of samples that it takes for good summaries changes based on what the summary happens to be. For instance, if I want the mean is well behaved, I can get a fairly accurate estimate of the mean with a fairly short sample. But if I want to summarize the variance or the standard deviation, I need a longer sample to have a fairly accurate version of it. And the reason for that is, if you look at, actually it's over here, if the width of this distribution isn't fully realized because I didn't sample it enough, I'm going to maybe under or maybe even overestimate the variability around that parameter itself as well. And I'll go a step further. If you wanted to calculate area under this, right? In our case, these are discrete samples. So really, if you were saying, what's the probability the mean is bigger than 170, you would just count the number of draws, samples that you had bigger than 170, and you get that probability. It's fairly straightforward. However, that shape of the distribution needs to even be more accurate, because if it isn't fully there, you have a little bit of a problem too. So what I would say in thinking about how long you're running your chain, that depends. Usually longer is better. Certainly you get a better estimate of the posterior distribution, but there is a place where there's a diminishing return. If you're just summarizing your results with means and standard deviations, that doesn't have to be as long as if you're taking critical values of that distribution or p-values or things that might depend on what we would call order statistics, which take a lot bigger sample to be stable. That sound good? I feel like I'm just yelling at you today. Should I stop yelling? Come on, Jonathan, quit yelling. All right, questions. Yes, Vladimir. Yes. Correct. Incorrect. No, R hat only tells us whether the chains, the time series, lie on top of each other. That's all R hat tells us. Mm-hmm. Correct, yes. Yeah, here, let me give you another example. So the question was, we don't have p-values. No, there's no p-value in our output. I want to talk about that in just a few slides. We only have R hat. Well, R hat, let me run this really bad model again and just show you what the R hat values for it would be. R hat 1.39, that was the beta 0. That was, let's see if I can find it, this one right here. And 1.22, that was for sigma. Even though most of sigma looked converged, this outlier right here moved the mean of its chain up to make the between chain variance higher, and that causes a problem. So R hat only tells us whether our posterior distributions from each chain have equal variance between and within, right? Generally speaking, we would like also R hat to be less than 1.05. There's some criteria for it. Back in the older days, it was like 1.1. More recently, it's like 1.05, 1.03. But this only tells us whether we should believe the result or whether we should run it more. So thank you for asking that question. Other questions? Yes, JC. Yes. The question was, if R hat's bigger than 1, should we make changes to warm up or a number of iterations of sampling? And the answer is yes. If you get an R hat that's much bigger than 1, I would say bigger than 1.05, I would extend the number of warm up iterations first and the number of sampling iterations. Make them both bigger. If it still happens, try again. If you get to a spot where they should be, like once you start running these models, you start to get a feel for how typical data happen to be, although data can be anything. If you still don't get convergence, that may indicate a problem with your model specification. It may indicate that the data don't support the model, what we would call under identification empirically. And in either of those cases, you may still be able to get a model to work, although the unidentified models you don't want to run at all. Those are sort of shouldn't be used. Unidentified model parameters, basically a dependency that's in the model that you don't realize would be there. You don't want that to happen. But the way that you get out of that situation is by making more informative priors. You can sort of force convergence by putting more information on the prior itself. What's happening when you have non-convergence is that the ratio that's being formed to accept or reject the parameter is being formed with a really flat either model data likelihood or prior likelihood. Basically, the whole posterior density itself is very flat. And so it may be the case by increasing the certainty in the prior distributions that you increase sort of a peak in your posterior distribution, which makes the estimation go smoother. But that's sort of the last resort. But that was a great question. Thank you for asking. Any other questions? All right. I believe we're out of time for today, officially, right now, 10:45. So I will stop here. I will thank you all. Actually, I just saw a question in the chat. Sorry about that. Once we have more predictors in the model, how will we know about the p-value for predictors? Stay tuned. We will tell you that soon. But I will say this. P-values, you can calculate, but a lot of Bayesians resent p-values, and I'll tell you why when we get there. More often what you'll see are what are similar to confidence intervals, although in Bayesian world, they're philosophically different slightly, and we call them credible intervals. And that'll be the next set of slides that we talk about next Tuesday. All right, everybody? Thank you for your question. Okay. Have a great rest of your week. If you have any questions, don't hesitate to send me an email. Try to get formative assessment 3 done by Monday, please. And I will talk to you next Tuesday. Take care.